Okay, good morning. Today we have the quiz. Before the quiz, I would like to finish one exercise and then we will start to have a quiz. So as as a problem I summarize in here for the stationary CVs. So last week we finished many exercises, and the exercise include the problem for the jets and fans, and the second is the nozzles and the pipe bands. So today, the final problems we meet for the stationary control surface problems is the velocity that is non-uniform flow. So the flow velocity is non-uniform, so we need to apply the integration operators. So what that means, if you go back to see the table summarize the general equation for the momentum equations. So the momentum equation include the integration operators for the control surface. So next we see the problems. So these are the problems is for the jack force testings, and the testing is operated in the wind tunnels. So the question tells us the tunnel is round with a diameter of 1 meters. So we know that we have the diameters is 1 meters for the tunnel, and the pressure at section 1, the pressure at the section 1 here is the 1.5 kilopascal. The pressure at the section 2 is the 1 kilopascal pressure, and the air density is 1 kilogram per meter cubic. Okay, and at the cross section 1, the velocity is uniform with the magnitude of 30 meter per second. So the V1 is equal to 30 meter per second. But at the cross section 2, the velocity is non-uniform velocity, and then the question tells you the velocity is linear velocity. So we go back to see the figure shown here. This is a linear velocity profile, and then here is the center. Okay, so please determine the jack force on the device and the support bands. And based on this problem, we neglect the viscosity resistance at the wall and assume pressure is uniform cross sections 1 and 2. Okay, so these are problems. The left-hand side, the velocity flow is uniform, but the right-hand side is non-uniform. And for this problem, we assume the flow is steady flow, so the momentum accumulation term is equal to 0. So we back to write down the momentum equations, and the accumulation of momentum is 0. So we know the sum of the force should be directly equal to the control surface integrations, and we have the rho and the v factors of the fluid, and multiply the capital V. The capital V is the velocity cross through the control surface dot small a cross-section area vectors. Okay, so for these problems, our target is the drag force, and this is the drag force. And for resistance, we have the force from the support fans Fs in here. So, and we have the pressures left hand side and right hand side. So we make the force balance along the x directions. So actually for the sigma F, what do we have? We have the pressure force dA multiplied the areas minus the P2 multiplied the area here, and we have the support force Fs, and with the direction to left, so we minus the supported force. This is the force balance along the x direction is equal to the momentum's flow. So the momentum flow for the momentum diagram shown here, we have the outflow and the inflow, and at the outflow cross sections, the velocity is non-uniform, so we need to use the integration operators on the right hand side, and there is a rho and the V2 square and the dA. So here we don't use the dot product because the normal factor of cross-section area is parallel to the flow velocity directions. And this is for the inflow, so we need to use the minus mass rate multiply V1. So first we didn't know the V2 velocity, right? We didn't know the V2 velocity. And we also didn't know the mass flow rate. Okay, so if for this problem, if we can know the mass rate and the V2 velocity, so we can solve the problem individually for the integration items and the inflow momentum. Okay, so first, we know that the areas for the cross section, because we know the diameters in here, so the cross section area is 4 over pi d squared. D is the 1 meters. So use the calculator to compute the cross section area. It's pi divided the 4 multiply 1. So here is around 0.785 meter square. And what is the mass flow? If we focus on the cross-section area, and this is the mass flow, we know equal to a rho VA, right? And the rho in here, we have the 1 kilogram per meter cubic, and the velocity on the left hand side is 30 meter per second. Okay, and the area here 0.785. So what is our mass flow is the rho is equal to 1 multiply 30 velocities and multiply the cross-section areas. So the mass flow in here is 33.56 kilogram per second. Okay, So right now we know the mass flows. So what is the V2? What is the V2? So as you see, the question tells us the V2 velocity profile is linear. So we assume the V2, we assume this is our equation 1, and we assume the V2 as function of the V1 multiply the slope. The slope K is the velocity gradient for the velocity profile in here. And we know the V2 velocity is also a function of the radius. What is the radius? We assume the center of the profile here is 0 point, and this is for the pipe tunnels. So along this direction is our radius directions. So this is, we know if the radius increase and the velocity increase also with a linear relationship. So we use the K indicate the slope of the velocity profile, and this is our radius, and the maximum radius is R0. So what is R0? The R0 is half of diameter 1. So this is 0.1 meters. So we assume this is our velocity profile. Functions for the velocity 2, and then based on the continuity equations, we actually know that the mass 1 is mass flow 1 is equal to mass flow 2. So assume the incompressible flow, we know the idea is the Q1 is equal to Q2, right? And it's indicated the V1 A1 is equal to V2 A2, right? So, but right now our V2 velocity is non-uniform. So we cannot use the equation by the V2 multiply the A2. So we need to use the integration operators. Here is the V2 dot dA. Okay, so based on these equations, we can try to solve what the K number in here. So we have the V1 A, the A is the cross-section area, is equal to the V2. So we write down the V2 equations is the V1 capital K slope and R divided R zeros. And what is the dA? Because this is the pipe tunnels, so the dA is can be replaced by 2 pi r. 2 pi r is the radius length and multiply dr. This is the ring area of the pipe. So, and what is the integration intervals? We start from the 0 here to the R0. Okay, so we just reorganize the equations. So we have the V1 in here. So this is the V1, and the A is the pi r0 square, right? and equal to, we move the constant outside the integrations. So the V1 is the constant, the K is also a constant, but is our unknown parameters. And the 2 pi also is the constant values, and the R0 also the constant values, divided R0. So inside we only have 0, 1 are zeros, and this is still have the R and the R here, so R squared and the dr. And we cancel out the V1, and we have the both sides have the pi, divided the pi. So, and we can move the R0 to the left hand side. So it's equal to R0 cubed. And the right hand side we still have the 2k, and this is integration is equal to the 3R0 cubed, right? So we cancel out the R0 cubed, and finally we know that the K is equal to 3 divided 2. Okay, so we have the K in here, so we can rewrite the V2 is equal to 2 over 3 V1 multiply the R divided R0, right? And since we know that R0 is equal to 0.5 meters. Okay, so right now we have the velocity and we have the mass flow, so we can go back to see the equation 1. So we put the mass flow and the V2 velocity into the equation 1. So, and then we can focus on our target is a supported force Fs here. So we also rewrite our equation only just take a support force on the positive. So we remove the support force to the right hand side, and the integration items minus n rate V1 move to the left. So we know that the P1A minus the P2A and the plus the mass flow V1 and the minus the integration rho V2 squared dA. Okay, so first we can compute the numbers for the integration problems. So we first focus on the target is the rho V2 squared dA. And the rho is, we have the rho is 1 kilogram per meter cubic, and the V2 function showing here. So we know that is the V2 squared, 1 multiply 2 over 3 squared, and V1 squared, and the R squared divided R0 squared. And we know that dA is 2 pi R dr. Okay, and we move the constant values outside the integrations, and we know the integration intervals still from the 0 to R0. So it's some constant value is the 4, and the 3 is the 9, and the V1 square, V1 is the 30. So it's multiply the 30 square, and the 2 pi is also the constant values, and the R0 square, we have R0 square over 1, and the inside we only have the 0 integration from the 0 to the 0.5, but I still use the R0 because we can easily to summarize the equations. And then the inside we have R cubic, okay, R cubic dr. Okay, so this is equal to, I use the calculator to compute the constant values. So the 9 divided the 4, then multiply 30, and then multiply 2, multiply pi. Okay, so this is the number is equal to the 1, 2, 7, 2, 3.45 R0 squared over 1 multiply. This is 4 over R0, 4 powers. So we cancel out the 2 zeros. So we only have R0 squared. And then finally, we know the R0 is 0.5. So we continues to multiply the 0.5 and the 0.5, and then divided the 4. So this is equal to the 795.2 Newton. Okay, so for the equation 2, we know the integration item is equal to the 795.2 Newton. So we go back to see the equation 2. So the support force is equal to the PA, P1A. The P1 is the 1.5 kilopascal. Multiply the A is the 0.785 minus the 1. The P2 is the 1 kilopascal. Multiply the area 0.785, and the plus the mass rate. The mass rate here is the 33.56. The V1 velocity is 30, and finally minus 795.2 newtons. Okay, so this is for the pressures is equal to the 1.5 minus 1 multiply the 1000. This is the pressure difference, and then multiply the area is 0.785. So for the contribute from the pressure difference is equal to 392.5 newtons plus the velocity V1 multiply the mass flow 33.56 multiply the 30 plus 30. So this is plus the 706.8 and then finally minus the 795.2. Okay, so just make the balance. The answer is around 304.1 Newton. So actually this is for the support force is Newton, the 304. But our question is what is the drag force? So we know the support force is along the left directions. So the drag force has the opposite directions. It's the positive. So 304 is our uh, drag force. Okay, and the support force is the minus with the same force magnitude. Okay, so this is our final exercise for the problem. We fix the stationary control volumes. Okay, so we wondering to move to the quiz. OK， 好，那我现在来说明一下我们的这个 quiz。好，那这次我们一样有2个题目。那之前2次的小考，大家还是有一些上传作业这个小考答案的问题，所以我想就是请大家再多多注意一下。那在考试之前，我今天也会稍微讲解一下题目。那因为第2次的小考，90分以上的人数明显的有变少一点。那我想可能是视讯的这个学习导致大家有一些学习上的效果的差异。好，那第一个题目我们在问的是什么？这个 tank 它有什么？我们知道它下面有开了一个阀，那这个阀会有水就流出去，这个阀的直径是4公分。那在此时此刻，我们有一个水深是3米。那我们假设这个阀下面这个底部摩擦力忽略不计，所以我们没有摩擦力，没有摩擦力。所以，请问一下，要花多少的力气去让保持这个 tank 维持不动？那我们知道，如果说这里有一个速度射出去，那 tank 可能会想要怎么样？往左边移动。那我们对于系统，我们要施加于一个怎么样的作用力，让这个东西tank 可以不动？那大家知道，第一个我们必须先算出这里的速度等于多少。那如果有速度，我们就可以用momentum 的平衡 ，momentum equation 的平衡。所以这个 v 其实就是我们的什么？我们的 outflow。那它会提供我们 outflow 的 momentum。那在这个时刻，我们就会假设在 control volume 的这个空间里面，因为是这个瞬间，所以我们假设我们的 momentum 在 CV 空间里面也是不变的，所以我们的平衡是会只剩下 force， 只剩下 force 跟什么？跟我们的 outflow 的 momentum 做一个平衡，对不对？好，那大家再继续思考一下，那这个怎么去做？这个问题怎么去做？我们想要问的是，要花多少力气才可以让 tank 维持在原地不动？好，这是第一个。那第2个题目，我们是一个弯管的，我们在考虑的是一个 pipe bend。那大家记得我们说，如果是 pipe bend 的话，因为它都还在管内，管内里面的话就会有什么？就会有压力。 所以我们其实会有压力在这个位置上，也会有什么压力在这个位置上。OK，所以我们都会有在端口端的 cross section one 跟 cross section two 都会有一个压力。然后看一下我们题目强调说它是水平放在地面上的一个水平的弯管，然后我们告诉你 D 这里有 D 是30公分，然后这个是里面是水，所以我们有密度是1000 kg 除上立方米，然后他说这个弯管里面的水流的速度，我们在这个地方是这个方向 E1，然后在这个地方是这个方向 V2。那我们告诉你说 V 其实E1速度应该就是0.5，sorry，我们有 V1 V2，那这里的话，它是跟你说流量是等于0.45立方米每秒，这是告诉你流量是这个。那他告诉你说这个 pressure 在 pipe 里面跟 bend 这个压力就是 P1 的跟 P2 的这个压力是100 kPa。那如果我们知道这个 bend 的体积是0.1立方米，然后它自己本身的重量是300牛顿。那请问，在这个系统里面的 Fax 的力有多大？然后在这个系统里面的垂直方向的力有多大？那也就是说，这其实会有一个向下的重量，水平躺在放在平面上地面上，所以它会有一个向下的重力，跟在水平方向上的这个 force 是来自于水流在管内流动所造成的，所以你要用多少的 Fax 的力量作用在断面积1跟2才能支持这个弯管是不动的。所以我们在这个力的平衡上，我们必须考虑的有压力，在管壁截面的压力跟最需要多少的这个 Fax 的支撑力去撑住这个弯管。那在垂直方向上，我们有这个管子重量跟水的重量，所以大家去找 Fax 跟 F 力等于多少。OK， 好，那请大家就可以试着自己去作答。那我们大概提示到这里，所以在这个问题里面，比较关键的是，那我们是不是应该要运用连续方程去思考一下，其实 V1 V2 是等于多少？好，让我们知道流量的公式是什么？流量公式不就是断面积乘上速度嘛？如果断面积一样，那是不是代表 V1 V2 怎么样有一样的这个速度场？那如果我们连续方程可以了解这个速度场，得到这个速度场，那因为我们回到动量方程里面需要去算这个动量流率，那我们有 in， 我们有 out， 因为我们假设我们的 control service 的边界是这样。OK， 那大家赶快去作答。OK， 那我把画面停留在这个题目1跟题目2。 好，各位把握一下时间，大概还有5分钟。好，我们时间差不多了，各位同学请把握还有5分钟的时间，可以去上传你的这个解答的这个过程。好，那我们今天就上到这里。